In the following slides, we will talk about aromaticity in general and about aromatic compounds besides benzene. All aromatic compounds have in common that they have usually large resonance energies so that they are particularly stable. And there's a general rule which defines when a compound is aromatic. And here we know that a compound is aromatic if the molecule is cyclic, planar, so the carbon atom should be sp2 hybridized, and it contains an uninterrupted ring of pi electrons, whereby the number of pi electrons should be 4 times n plus 2, whereby n can be 0, 1, 2, 3, and so on. And this rule is also called Hückel's rule because the chemist Erich Hückel defined this rule to identify if a compound is aromatic. And if we talk about aromatic compounds, we can also name it as annulenes, and then in front of this name we normally set the number of pi electrons. So, for example, if we have benzene, we could also say it is 6-annulene because we have 3 double bonds and each double bond contains 2 pi electrons, and we can call 1, 2, 3, 4, 5, 6. It means we have a general number of pi electrons of 4 times 0 plus 2, and this is then an aromatic compound. If we go to the next example here, we can see that 14-annulene is also an aromatic compound because we have only sp2 hybridized carbon atoms here, and we can see that this molecule is planar and cyclic, and we have an uninterrupted ring of pi electrons. If we then look at the next example, which is called 10-annulene, you could expect that this molecule is also aromatic because you can see we have 10 pi electrons. That means we have 4 times 2 plus 2, so the amount of pi electrons is fine. And then we can see we have an uninterrupted ring, and we just have sp2 hybridized carbon atoms. However, what is now important is that we have here a steric strain between the 2 hydrogen atoms, and this is very important to recognize because then, due to this steric strain, the 2 internal hydrogen atoms prevent the ring from being planar. The rule that we should have a planar compound does not account for this molecule, and this molecule is not stable. So in general, we can say about aromatic compounds that these compounds are particularly stable and they have large resonance energies. Well, and then this is the first part of aromaticity, and if we go to the next part, we can see that aromaticity is not mandatorily assigned to a neutral molecule, but we can also see charged molecules which are aromatic compounds. So the simple case here is cyclopropenyl cation, where we only have 1 double bond which contains 2 pi electrons. Then we have a positive charge here on the carbon atom. And now you can see that this carbocation has an empty p orbital left. And this p orbital can now interact with the double bond because the orbitals are very close to each other, and hereby the molecule gets stabilized, and that's why we have an aromatic character. If we go to the next carbocation, we can see that we now have cycloheptatriene as cation, and we have 3 double bonds here. And if we would not have this positive charge here, then we would see that the ring of pi electrons would be interrupted here, so the compound would not be aromatic. But now, as we have a carbocation, the carbon does no longer have 2 hydrogen atoms attached, so this is why we can now say that the carbon atom has an empty p orbital, which becomes part of the aromatic system. So, and we can have an overlap with the p orbitals, so the molecule is stabilized, and this is then an aromatic compound. And in general, we can say that this molecule will be easily formed because there is a certain preference to get this stabilization when it gets aromatic. So we can say that the extraction of this hydrogen will be very easy. Similar to the positive charge, we can also have a negative charge in the system. For example, here for the cyclopentadienyl anion, and here we can see that we have again two double bonds, which makes for pi electrons, and then we have this negative charge here on the carb anion. Hereby we have two additional electrons, which are now part of the pi ring system. So in total we have 6 pi electrons, and the pi electrons are again delocalized, and this is why this compound is also aromatic and quite stable. Here we can see again how it looks like. So we have the normal double bond here, and then these additional 2 electrons due to the negative charge, and then in total we will end up with a ring system above and below the plane. What do we learn here is that aromatic compounds can also be charged. And then we can have again a look on the cyclopentadienyl anion, and we can see that this can be formed by a deprotonation step of cyclopenta 1,3-diene. And a molecule is shown here. So this cyclopenta 1,3-diene is not aromatic because we can see here is an interruption of the pi ring. And then if we want to deprotonate one of the hydrogen atoms here, then we will end up with the cyclopentadienyl anion, and there is a resonance if we want to draw the negative charge here. And as you can see, there are several possibilities where the charge can be. That means this structure has a delocalization of the electrons, and in turn this means that it is quite stable. And this delocalization can also be drawn as these 2 rings of pi electrons above and below the ring plane. And this example shows why we can expect that this protonation is quite easy. And this is because we end up with a very stable resonance structure of this aromatic compound. And yeah, in general, we can say that the high stability of aromatic compounds is connected to a very easy preparation of these compounds. And another possibility for aromatic compounds is that they can contain heteroatoms. For example, if we have a look on furane, then we can see that this molecule has already 2 carbon-carbon double bonds, and then we have 1 oxygen atom, which is part of the 5-membered ring. And in order to fulfill the Hückel rule, 1 lone pair of the oxygen atom, these 2 points here, is part of the pi system. In this way, there is an overlap of the p orbitals in order to realize the delocalization of the pi electrons, and hereby the Hückel rule will be fulfilled. Another similar system to furane is Pyrrole. You can see we have again a 5-membered ring, and we only have 2 carbon-carbon double bonds in this ring, but we have 1 nitrogen atom which has a lone pair. Now the lone pair of the nitrogen atom contributes by overlapping with the p orbitals of the carbon atoms to create the pi ring. And in this way we get again 6 pi electrons which are delocalized in Pyrrole. And here you can see the orbital scheme of Pyrrole. We have 2 carbon-carbon double bonds, and then we have the lone pair of nitrogen. Finally, based on the overlap of these p orbitals, we end up with 6 delocalized pi electrons in this ring. If we talk about pyridine, the situation is a bit different. So we already have 2 carbon-carbon double bonds and 1 carbon-nitrogen double bond. And this time we have a 6-membered ring. That means we already have 6 pi electrons, and therefore the lone pair of nitrogen does not contribute to the pi system. Accordingly, the lone pair of nitrogen is available for other reactions. And if we look a bit closer on the orbital scheme, we can see it more pronounced. You can see here the overlap of the p orbitals will lead to the characteristic delocalization of the 6 pi electrons. And then additionally, we have this lone pair of nitrogen. And this explains why pyridine is much more basic compared to, for example, pyrrole. In pyridine, the lone pair of nitrogen is available for other reactions, so it can, for example, act as base, can withdraw a proton, while for pyrrole, the lone pair is not available as it is part of the aromatic system. So adding a proton would destroy the aromatic system, and hence pyrrole is much less basic compared to pyridine. So to summarize, aromatic compounds can also be charged or contain heteroatoms.